All right, I just want everybody to know that we're on the hour and we're going to give maybe 2 more minutes for people to join. We've had a surge of registrations in the last week, the last day, the last hour. So some people are just getting their login instructions. But you are in the right place. This is the Westgard web on the total testing process. All right. Let's be respectful of everybody's time. We're going to start with our webinar. Our focus is on the total testing process, and we can go back to 1981, where Lundberg came up with the brain-to-brain loop. So that started in everybody's mind to discuss all parts of the testing process, not just the part in the laboratory, not just the moment where the machine makes its reading and produces a result. Instead, this involves ordering and collection, identification, transportation, separation, analysis, reporting, interpretation, and action. Brain to brain. And if you look at this particular copy of the total testing process, you'll see the pre-analytic section. All the different points that talk about pre-analytic are actually half of the circle. The analytical section is just analysis, and then only 3 points are where it's post-analytic. So the pre-analytic part of the total testing process has grown to dominate the thinking and the attention of the field. These errors are important because we have recent publications saying 795,000 Americans die or are permanently disabled by diagnostic error every year. Now, our previous shocking estimate came out of the Institute of Medicine report, To Err is Human. That was back in 2000, and that was saying about 100,000 people die from medical errors. Now, this new estimate is including not just deaths, but other kinds of injuries. And but on the other hand, it's narrowing its field to saying diagnostic errors. Another recent study that's been talked about is looking at these error rates and figuring out what that means on the sigma scale. So we're going to talk a lot about Six Sigma as a way of benchmarking the acceptability and the success rate of different processes. So some of you, I hope, are already familiar with Six Sigma and what we'd like our metrics to be, 6. Others, I'll just give you the quickest introduction. Below 3 is not good. 3 is the Minimum acceptable, 4 is good, 5 is excellent, 6 sigma, that's obviously the ideal, that's almost perfection. Here we have a study of 29 US academic medical centers finding out missed or delayed diagnosis rate is 23%. That's almost 1 in 4 patients are being impacted by a late diagnosis or a misdiagnosis. That works out to be a 2.2 sigma process. And then if you look at causing temporary or permanent harm, well, we don't, obviously that is smaller, but it's only 3.2. It's barely acceptable. Of these various parts of the brain-to-brain loop, what is going to have the most impact on inappropriate patient care? Do you think it's going to be pre-analytical, the analytical, or the post-analytical? The studies that have been coming out across the decades tend to weigh down, they give the verdict, oh, it's pre-analytical. So we go back to Ross and Boone, a conference abstract, 46% of errors were happening in the pre-analytical. Plabani, the first landmark, I should say, paper on pre-analytical errors, 68% happening in the pre-analytical, and then you follow that up another decade later, 62%. Where are the least amount of errors occurring according to these papers? In the analytical section. So it comes out, what's most important, or where are the errors happening most? They're happening in the pre-analytical area. Analytical is the smallest of analytical occurrence, and then post-analytical, that's the second highest rate of errors. And that's the thinking that has dominated the field, the literature for probably the last 3 decades. That what's the problem? It's pre-analytical. That's where we need to focus. So we have this kind of hourglass of stress and emphasis. Pre-analytical, most important; analytical, least important; and post-analytical, second most important. But as the papers roll in and the focus of the study continues, it really is an emphasis on just the pre-analytical, as this is where we need to make all of our efforts. But really, any point in this is going to be a choke point. That is, analytical, you can't ignore it. You can't say, all of our errors happen pre-analytically, we don't have to worry about analytical. You do. It's every part of the process is important. You can't solve all your pre-analytical problems and ignore what's going on the instruments and in the actual analysis. If you ignore that, it will bite you in the end. One of the reasons that we see more emphasis on the pre-analytical step is they tend to be very tangible, very tactile, visible errors. When you have a grossly hemolyzed or a lipemic sample, it's right in front of you. You can see what's going on. If you have a missing sample, it's you know there's something that is missing. On the other hand, the analytical error it's almost an intellectual error. You have numbers, so the system is generating numbers, they're giving you results, but through your mental processes, you determine that the number that you see, that's actually the wrong number. So it's more difficult to envision what an analytical error is. The other way that errors occur pre-analytically versus analytically, if we talk about a lot of the pre-analytical errors, they happen in single instances. So one sample might be lipemic, the other sample might be hemolyzed, but it's not, oh, the whole run. Every sample we took today was hemolyzed. Systematic analytical errors, which when we do QC, those are the errors we're really worried about. Those they could impact a whole run. That whole run could be an entire day. In the cases of point-of-care devices doing IQCP, being out of control on QC when you're doing it once a month, if you're out, that means a whole month of data, of results, could be invalidated. So there are different impacts to the kinds of errors that we see. We've only really been looking at point of care or let's see, total testing processes on the Six Sigma scale since the year 2000. Six Sigma as a quality management approach that was introduced, in the 1990s. It took a decade before it really penetrated into the laboratory, and I would say it was introduced in the year 2000. But the major advisory groups, IFCC, on pre-analytical error, they say when you look at pre-analytical processes, you should put it on the Six Sigma scale, because our own regular perception of an error rate is different than what we need to do as a system. If we, as an individual, we say, oh, there's a 1% chance of something going wrong, usually we think, oh, well, that's really great. In my experience, that means 99% I'm going to get the right answer in my own healthcare experience. But as a system, if you say, oh, 1% of all of our results are going to be wrong, that's a very different way of thinking, because you're not saying, am I going to be lucky and miss the error? It means I'm going to have errors. And how many of them am I going to have? A 1% error rate on Six Sigma is just above 3 sigma, just above minimum. And Six Sigma is saying, no, you need less than 4 defects out of 1 million reportables. So achieving Six Sigma is really, it's quite an accomplishment, but it also means you deliver an extraordinarily good level of quality. So when David Nevalainen and his group did the first translation of quality processes into Six Sigma metrics, he was he looked at the College of American Pathologists CAP-Q probes. And so order accuracy, how did that translate? Well, it came out at about 3.5 sigma. Therapeutic drug monitoring, that was below 3 sigma. Proficiency testing was about 3.9. The best number that came out was almost 5, and that was the ability to report the correct results. But there were no Six Sigma processes when Nevalainen did his study in the year 2000. So it was I suppose it was a moment where you could say we were crestfallen. Laboratories had a pretty good opinion of themselves, and they might have said, oh, if we asked a lab, oh, are you Six Sigma? They said, well, maybe I'm 5 sigma, maybe some 4, but I'm very good. And we were off by a couple orders of magnitude. So that did lead evidence that these pre-analytical processes need some improvement, need to be focused on. And then this is about 2014. So we've had almost a decade and a half of focus on pre-analytical errors. Let's again give ourselves some context. Airline safety in the US is Six Sigma. We have very few crashes. Baggage handling is in the 4 sigma. About 1 out of 300 bags is taking a different vacation. And departure delays, about 30%, is less than 3 sigma, 2.3. Now let's fold in our own experiences This is, again, a laboratory in Italy. Does the request come in, the test request come in with all of the right information? Well, that's coming in at over a 5 sigma success rate. Does the sample come in with enough volume to run all of the tests? A high 5 sigma. Hemolyzed specimens 4.1. So again, that's like your baggage handling in airlines. About 1 out of 300 samples coming in and being hemolyzed. Inadequate anticoagulation ratio, chronic problem coming in at 4 sigma. Then, how often were people out of control? What's their QC? Oh, that was 3.7. How often were people failing their EQA? That was 3.6. So when we started looking at things on the sigma scale, and we got in, I suppose you could say the pre-analytical processes had seen a rapid improvement, and so their metrics went up. But in the meantime, all the focus on pre-analytical quality had meant we're just going to take analytical quality for granted. You don't need to improve that. It's a very small percent of our errors. Well, our labs were still failing QC and EQA at pretty high rates. Here's from a laboratory in Romania, same year. Their patient ID errors were 5.3, missing data, so same as we saw in the previous slide, 5.6 sigma. Samples being lost was 4.8. Anticoagulation ratio was 4.8 instead of the 4 that we saw in Italy. Hemolyzed specimens was about 4.2, very similar to what was in Italy. Clotted samples, 4. And then it just happened that this particular laboratory gave information on LDH and sodium methods. So these were 2 methods, and they had a 4.5 sigma for LDH, but then a 3.5 for sodium. So it's one of the few studies where you had all of the pre-analytical processes benchmarked, but you also had the analytical quality on a test-by-test basis. So if we add that up, and we from both of these studies, we know the test volume. So we can say, what was the sigma, what were the percent errors, what was the test volume, how many errors were being generated in different places. In the Romanian laboratory, they had almost 4,000 analytical errors and only about 1,500 pre-analytical errors. In the Italian laboratory, they had almost 32,000 analytical errors, whereas in the pre-analytical side, it was only about 19,000. So there are big distortions in how we look at quality. And then just another notice, this is what Theranos quality results were. So this is their QC rejection rates translated into Six Sigma metrics. So they had the sex hormone binding globulin that was being rejected by QC 87% of the time. So that comes in at 8.4 sigma. And you see all of these different QC of methods, they're all coming in below 3 sigma. Remember, some of you may not know what Theranos was, but it was a $9 billion value company. It went to 0 value. It went out of business because of these quality concerns. And 2 of their executives ended up spending, well, they are sentenced to more than 10 years at federal prisons. So having your sigma metrics down very, very low can result not only in harm to patients, but also they can put you out of business. They could put you in jail. Now, in another more recent study, it was a meta study looking at different um, error rates across Africa. And I want to point out the variability that we see from study to study, or you could say from country to country. So two studies from Egypt, one saying only 5% pre-analytical error, the other saying 43% pre-analytical error. In Ethiopia, the difference is, well, 10 or 29%. A study in Kenya saying only 2.7% pre-analytical errors were occurring. So there's a lot of variability, you could say, in the studies, but also in the places that they're looking. So we might have a perception that pre-analytical errors are the only thing, and they're the most thing. It's going to depend on your facility. What are you looking at? And even maybe what country you're in, what resources are available to you, what level of staffing and skill in the staffing is available to you. So the conventional wisdom might be an interesting starting point, but you have to check it out yourself and know what your own sigma metrics are, know what your own error rates are. Here's something from the United Kingdom. This is a point of care device and the different kinds of errors that occur. Is the sample being overfilled or underfilled? Is there enough of the sample? Are there problems with the batteries, the barcodes, the cartridge, the analyzer and motor? So you can see the point of care, there's a lot of different kinds of errors in these small devices. And it's a greater challenge with point of care with smaller devices because they frequently end up in the hands of people who are also less skilled. And in areas where there is less emphasis on quality and more emphasis on speed and more temptation to cut corners. Now this particular study, they did an overall. So they broke out all the different kinds of error, and then they said, well, overall we have a 6.5% error rate, and that is just barely acceptable. It's overall it's a 3.1 sigma device in terms of its ability to successfully generate results. Now here's, I would say this is the most recent definitive study from the IFCC working group, and they're looking at this group has defined very specifically, here are all the different kinds of errors that occur in the pre-analytical phase, in the analytical phase, in the post-analytical phase. And if we jump, let's say they have specifics on single tests for their turnaround time, and those can often be quite low, but for ones that are more lab-wide, you can see I've put the numbers on the worst error rates. So we've had a 2014 look that said QC and EQA, they were the lowest performing, most error-prone processes across the total testing process. What about 2021? The two lowest performing processes, IQC and EQA or proficiency testing. Those continue to be the biggest sticking points in our total testing processes. Another one, hemolysis. If anything, it's a little sad because our hemolysis success rate, we saw in previous studies, it was in the 4 sigma zone. Here, this study is saying 3.71, 3.75. That's the two different ways that you're doing your hemolysis check. Turnaround time is 3.75, so just above that. Everybody complains about the turnaround time, and the turnaround time, I would say, is in some ways an unfair benchmark because it is it's subjectively decreased continuously. If you can make a 1 hour turnaround time consistently, then your clinicians and your customers will edge you even shorter. They will say, oh, well, now that's the standard, well, then I want it at 45. And they will keep doing that. And so you find that that metric keeps getting a low number because you keep having the demands increase. I should note this particular set of sigmometrics, this is the 50th percentile of their surveying group. So they look at a bunch of laboratories, they collect in this program measuring these processes, and then they'll break out, well, here's the 10th percentile, and there's the 90th percentile. This is the 50th. So this is what, let's say, most, the average laboratory, their biggest problem is QC. Their next biggest problem is passing proficiency testing. The costs of all this. If you want more ways to motivate your administration to helping you to improve this. So here we have a study. This happens to be from Turkey. They worked out, I made the trend, I did the exchange rate, so it's out of 32,783 samples that they looked at. The costs added up to $77,000, about $235 per test. So every error was costing them almost $2.50. And then, well, you might have made the exchange rate, but I would say if you move this to a first world, or if you moved it into the United States, that number would undoubtedly go up because the cost of labor is more expensive, the cost of the time, everything, all of the inputs are probably more expensive in the US. Again, let me break down a little bit of the emphasis. So this is the 2007 paper by Plabani, and I should just say the Plabani, this first one and his follow-up, the 1997 and 2007. These are like the landmark papers on pre-analytical quality. From it, all other emphasis is born, and these two papers get quoted quite a bit. So in his study, he was looking at 51,000 tests, from which 393 results were the questionable. 160 of those were lab errors. And of the lab errors, 46 caused inappropriate, 46 of the test results had inappropriate patient care, and 24 of those were caused by analytical errors. In other words, analytical errors are still more than 50% of the major inappropriate care coming out of Plabani's paper were caused by the analytical errors. And you can kind of understand, remember, since the analytical error is, even the erroneous number looks like a number. So it will move past a lot of the steps. If you have an error and it's happened in the specimen, if it's a physical issue, you tend to catch that. But the number can get all the way out to the patient and cause the misdiagnosis. It's more often the time that we have difficulty detecting it. Plabani also even noticed that, said in that paper, well, even the rate of analytical errors that we found, it's probably an undercount. We underestimated the number of analytical errors because we have a difficulty actually detecting what the error results are. When is an analytical error actually occurring, and does our QC system work correctly to detect all of the analytical errors? And someone who's spent 30 years working with laboratories, a majority of the time, labs are not designing their QC to actually detect real medical errors. They're missing things, or they're causing false rejections for no reason at all. Now let's talk about the total testing process. Again, we're going to narrow down to the point of care. Point of care, we have staff that might not have the skills, that want to cut corners. They're feeling the pressure. I need to get this result quickly. The device is not built to do traditional QC as well as our core laboratory methods. So it might say, well, we have, there's some lights on this device, and they'll light up if something goes wrong. It might just be a voltage check. If it's an electronic check. So often that gives a false sense of security to people, like, oh, see, the device is going to tell me. It's got onboard built-in QC. Most onboard QC in most point of care devices is not sufficient. It only covers a very few number of steps, often only in the reading out, display. Traditional statistical QC, that covers much more. It's going to cover the sample steps, the sensor steps, and the readout. If you go even further, you're using tonometered blood to do something, that'll cover even more of the sampling. Using patient sample replicates as your QC samples, that's a bit, that's pooled patient samples. That will start to go into the pre-analytical factors, because now you have really essentially a patient sample. It happens to be a QC, and you can put it through the system, and it'll be treated even on the pre-analytical side as a patient sample, so you cover it even more. So you can have certain steps that you take for QC, and they will cover less or more of the total testing process. If that sounds a little too confusing, let's switch gears and let's talk about driving. Okay, you have a car. You turn on the car. There are a bunch of you might have a screen with a bunch of different indicators. Is the oil pressure okay, or is the check engine light on? And yes, that's important. If you have a light that says your tire is flat, important to know. But that doesn't guarantee, if none of those are going off, doesn't guarantee that you're going to be a great driver. Doesn't guarantee that you're not going to drive the car into a ditch. If you want to test the car itself, you're going to get a new car, you take it for a test drive. Well, it's going to now look at just, okay, is the motor working, but also does the vehicle itself function correctly? If you are driving and you get caught for speeding, well, that's the traffic monitoring element of our police force. We have also sort of our pre-analytical steps are who gets to drive, and what conditions should you drive in, and what should you be on a particular side of the road to prevent you from crashing into other cars. That comes with operator licensing. So that's getting your driver's license covers even more of the total driving process. And then forcing you to get your license renewed, then that means, well, if you have gotten some tickets, you've been in some accidents, at a certain point they'll say, sorry, you can't drive anymore. So different steps we take monitor different parts of the testing process or the driving process. Now let's return to our error rates. Here we have something from Pakistan. This is a relatively recent study. What is the biggest source of pre-analytical error for them? It's hemolyzed samples. Another study from last year, the global blood specimen rejection rate. Another meta-analysis, they're looking at multiple studies. They have the most number of studies from Southeast Asia, and that rejection rate is coming in at 3.4 sigma. Africa, they only had 4, but those 4 studies showed 3.6 sigma. Europe, they had 7 studies, 3.8. America, they only had 4 studies, but it came in as the best, 4.1. They only had 1 study from the Eastern Mediterranean, it was 3.7. They only had 1 study from the Western Pacific, it had the highest success rate for blood specimens. So again, meta-analysis can be good, but I have a feeling the best blood specimen rejection is not in the Western Pacific. We can say right now, based on the data we've seen, America might be leading. But it does also seem like in the 3 to 4 sigma, that's where specimen rejection rates are globally. All of this is showing a high degree of variability, isn't it? So it's hard to say, yeah, errors are only going to happen 65, 2/3 of the time, they're always going to be in the pre-analytical. To quote Tolstoy, happy families are all alike. Every unhappy family is unhappy in its own way. Labs that get 6 sigma for their processes will probably be all alike. But if you have a lower than 6 sigma metric for one of your pre-analytical process, it is probably going to be unique. How your processes fail are unpredictable, but also they're probably local. Could be local in the sense of what are the skills of the staff available to you at that facility based on where you are in the world. That also means some of these solutions are going to have to be local. That is, we can't generalize too much because how you succeed is going to be an individual path. But we will try and generalize nevertheless and say, how do we tackle pre-analytical errors and try to reduce them? And it comes down to, well, you're going to need time, you're going to need effort, you're going to need money. And then if we're really blunt, it's all money. If you want better staff, more skilled staff, you have to invest in them more. You can train them, train your staff, but that's an investment of your time. That's still going to cost money. You can build a culture in your facility, in your laboratory that really motivates people so that they're better at adhering to standardized operating procedures and being dedicated to doing everything right. But culture, it's not free. Culture is still an investment of time and resource. And then money, it can come down to, oh, do we have the right needles? Do we have the right devices? Do we have devices that can do an automatic detection of it, or we can automate in some ways a step that is prone to errors? So these are more specifically ways to address in general pre-analytical errors, standardizing your operating procedures, having training, having not just written down, but going through the effort of building the standard, automation, and then re-engineering things or redesigning things, or lean. I'm not going to spend time talking about lean because you can find that in many, many places. Sorting out your closets and building Kanban and all that stuff. There are lots of people offering lean. To try and make it a little more specific, I'm going to go after one of the biggest, some say the biggest pre-analytical error source, and that's hemolysis. It's the most common pre-analytical error and accounts for over 60% of clinical chemistry sample rejections globally. So if we could figure out ways to reduce hemolysis, that would have an outsized impact. The costs of hemolysis, again, there are studies out there. One from a US hospital that has 650 beds, they said they figured it's $1.1 million a year. Now that's, I should say, that's not hemolysis, that's all pre-analytical errors. And that works out to almost be 1.2% of the entire hospital operating cost, pre-analytical error impact. Something a little more focused, just looking at hemolysis. This is from a UK study, but I did the exchange rate. So in 2012 dollars, it was $82,000 a year if you have a hospital that's taking in 60 patients, 60 new admissions a day. A large urban ER, this is in Italy. I'm making the translation, the exchange of 2014 dollars. It's almost $26,000 a year. This is just the ER. And in that ER, they had hemolysis rates up to 29%. And almost a quarter of their sample collection costs were being consumed by the problem with hemolysis. So there are a lot of costs. It's worthy of specific focus. You can see there's a difference between it happening in the ER and other parts of the hospital. So here in an emergency department, they have the point of care devices, they have the staff that may not be so focused on laboratory quality and instrument quality and so forth, and they're getting 3 or below 3 sigma with their hemolysis. In the ICU, where they probably have a little more focus, a little more skill, we're at 3 to 4 sigma. Here's a study from Turkey saying, okay, can we train ourselves into improvements on our hemolysis rates? So they did a study. We're going to do some regular training. We're just going to do, an in-service. We're going to have a 1-day. Hey, do you remember how to draw blood correctly and mix the tube correctly? And then the other option is we're going to do intensive training. We're going to train you twice a day. We're going to come and look over your shoulder up to 4 times a day to make sure you're doing this right. And that's just focused on the ER. What they found, well, the regular training had a modest impact from 4.3 to 4.5 sigma. The intensive training went from 4.4 to 4.8. So there was more intensive training, you get more benefit. You're reducing your defects per million by 828 in the regular scenario, or 1491 defects per million in the intensive training. What if we could automate something? Let's move away from having to eyeball the sample and making a visual check on hemolysis to an automated HIL check. Here we see out of 306 samples, 150 of them were considered hemolyzed by visual. So that's a 1.6 sigma. They go to a automated check, it drops. They've got more than 100 more samples that are considered not hemolyzed. So that jumps to 2.5 sigma. On a defects per million scale, that's 300,000 less defects per million. So that automation delivered a much larger benefit than training. Now, that is not to say that automation is a guarantee, that just automating everything is automatically going to make everything better. In a case, a different Turkish study, they had a 4.1 sigma using the visual, but when they put on the automatic, it actually 3.5 sigma. So your sigma went down probably because the system is catching more errors, and you have to look further upstream. We're catching more hemolyzed samples. We haven't addressed what's producing those hemolyzed samples. More common ways that you can reduce hemolysis: try not to use syringes or draw the blood too vigorously, or collect through an IV catheter. Be careful if you underfill the blood tube, you've thrown off the ratio of the blood to the additives. Don't take a capillary sample. If you over or under mix the blood, the tube, either one can impact hemolysis. If there's too much time between when you collected it and you centrifuge it, if you have a tube system and there's some sharp turns, or there's extra vacuum and you're putting too many G-forces on the tube, that can also impact hemolysis. If you're doing a centrifuge and you use really high speed, or you do it for a very long time, that can also induce hemolysis. Now, these are things where we can actually, if we standardize, we build an SOP and we train people, okay, we're going to avoid these ways of drawing blood, we can lower the hemolysis rate. Other solutions, there's a relatively recent recommendation that we should have our own QC. We should have QC that just looks at H indices. There are commercial vendors that offer that. Not a huge number of them, but it is offered. The pre-analytical work group of the EFLM has said, if you can't buy them, here's how to prepare them. Here's the recipe. Build your own indus, serum indus QC material, and they think you should run it twice a day. So more often than your analytical controls, they want you running controls that could detect icterus, lipemia, and hemolysis. And then there's also an EQA. You could do a proficiency testing where the materials being sent to you are serum indices, and you're trying to detect, CAP, or somebody is going to send you a sample and you're going to determine, okay, is it hemolyzed or is it not? Those are all other different ways to tackle and identify where you have problems. Then, another good point is not every sample which has some amount of hemolysis is a sample you have to reject. Depending on the level of hemolysis, some results might be still good. Some results could be reported with an asterisk and a caution, and still other times, okay, if there's too much hemolysis, yes, you can't run the sample. And this is, I reference this is the critical reviews. When we first started talking about hemolysis, the first quotation, the first reference has this says a decision rule set on how to determine whether or not results are useful. It's very faint. It's also very faint in the paper itself. This is one of those, I don't think I can do it justice. You have to get the paper to see, here's your guidance on when can you still use a result that's coming out of a moderately or minimally hemolyzed sample. So let's wrap up what we're talking about for hemolysis, and then try to extend those actions to pre-analytical errors in general. So the most vulnerable places for hemolysis are typically at the point of care, and a lot of point of care devices, they haven't built in anything to capture hemolysis. They're not even trying to detect hemolysis. They put all of it on the point of care user itself. That, would be nice if there were devices out there that can do the hemolysis check, even if it's a smaller device. So in places at the point of care, in the emergency room or emergency department, the staff are often pressured to, let's get the result, let's do it fast. We're going to cut corners. We're not going to do it perfectly. We just want a number. So they're particularly vulnerable. Training, getting the staff to understand. Another challenge with the training is you can train once, but to sustain the training, if you think, okay, how do we make sure the staff that we train this year are still going to remember and implement the right thing next year? And how much is our staff turnover? Because having a constant influx of new staff or traveler temporary staff, how to make sure those people also are getting their training. So training is not a one-time thing. It's a long-term investment that you have to make. Other things, putting that emphasis on the standards, purchasing where possible devices that have automated checks. The recent conclusions is the visual checking of hemolysis is highly variable. The individuals come up with different decisions, so it's hard to even replicate. Even within individuals, on a different day, they might have a different decision about the same type of sample. So pursue the places where you can find technical and automated checks when that's possible. Figure out what things you could avoid doing that are at the root cause, the source of those pre-analytical errors. This will end up being a kind of unique journey for each laboratory. And then remember, pre-analytical errors, visible, tangible, tactile, predominant in your field of vision, but make sure the device is also analytically sound. It's a shame to do all this effort and get the sample to the device, but then the device itself is poorly engineered and it's going to give out the wrong number anyway. And with that, I do want to draw this to a close. This is the moment where we have time for questions, some housekeeping things. This is being recorded, so there will be a recording that you can view for about a month. That link I will send to you on Monday. So you will get the link on Monday by email. Second thing, this is accredited for 1 hour of ASCLS PACE credit. On Monday, you will get instructions on where to go on the ASCLS website. So the website will say, enter some information, then enter an evaluation, so you get to grade me and the material on whether it was helpful. And then at the end of that, you go through the feedback, and then you can online generate your own certificate and download it immediately. All right. One question that has come in. Also, for those of you who wish, you have to send me an email if you want a PDF version of this. I don't do it blanket, I don't like to send PDFs out to everybody, but if you really want it, contact me. I will give you a PDF version of this for you to review and have as your personal record. So one question came in is, how do you determine the sigma metric of a method? So every study, when they look at a pre-analytical process, they will look and they will calculate an error rate. It's 1% error, 0.01% error. You take that number and you move it over to a Six Sigma table. The Six Sigma table just gives you essentially a lookup. 1% error, that's 3.6 sigma or something. So you can look that up, and we just done all of the translations because rather than focus on different error rates themselves, we want to focus on what is the acceptable error rate. So if we use the Six Sigma standard, we all know, oh, 5 sigma is excellent, 6 sigma is where we want to be. Ultimately, ideally, if it's below, if it's 4 sigma, well, that's good. And 3 sigma, that's the minimum acceptable performance. If it's below 3 sigma, we're really worried. That's too error prone. We want to be targeting those for improvements. All right, let me take some other questions. Let's see if I can move this here. How can we avoid IQC pre-analytical errors? Well, I guess IQC pre-analytical error, they're two different steps. Now, in some ways, if you're doing IQC, so you're running your controls, when there are steps involved in preparing the control, some of those, if it's a liquid control, then you put it into the system like a patient sample. So if you have problems getting specimens onto your instrument, that's a pre-analytical error that could be caught also by your handling of IQC. But I think a lot of the argument about IQC is it focuses on the instrument and the method itself, and some pre-analytical steps are just, they can't be covered. You can't barcode errors or insufficient sample, insufficient volume to run all of the tests. Those are errors that traditional QC, analytical-based QC will not catch. So analytical QC, just running controls, doesn't mean you don't have pre-analytical controls. Having your values come in on your controls doesn't necessarily mean you have a perfect testing process. Commercial external quality control available for serum indices. Yes, I'm trying not to make this a commercial activity, but yes, at least one of the major control vendors sells that kind of control. And also the number of programs offering number of EQA proficiency testing programs, that is a limited set. I don't want to get too commercial, but they are out there. When we perform EQA and notice poor performance, if the EQA materials are not commutable, is it appropriate to adjust the result factor on the instrument in order to adjust the result to the EQA results? So are you just trying to shift your instrument so you get the right answer in your EQA? So if you find you have a bias working with EQA, you do need to explore, is there a reason? How commutable is the sample? I mean, a lot of the EQA providers are pretty good about the matrix, and the samples are more commutable than our traditional control materials. So, I mean, I would say you need some kind of additional confidence that, yes, the number that is being received in the EQA result is more commutable and represents a true issue. I mean, you could see, are you finding results from patients being biased in the same way, in the same direction, of the same magnitude? That would be another check for you. Came in twice. Someone's asking about the Westgard fashion. We don't sell those retail. Typically, we don't give those away. Yes, so you kind of have to have a really good connection in order to get a Westgard QC polo or quarter zip or anything like that. So I guess those are all of the relevant questions for the moment. You have an email address, so if there are other questions that you're shy about asking, or they come to you later, please send them to sten@westgard.com, and we will, if we have enough of them, we'll put together an article, we'll put it on westgard.com in our questions section. And I do want to say next month there is another Westgard Zoom. It's going to be on detection limit, things like limit of detection, limit of blank, limit of quantitation. When do you do these things? How do you evaluate those things? We'll be covering that. And then 2 months from now, at the end of March, we'll be doing a QC-focused talk. It'll be on what we refer to as blind man QC. It's about what happens when you use ranges that are not appropriate. A manufacturer's range that's too wide, or you build a range out of a system of multiple laboratories or multiple instruments, and you try and build a range that covers them all. What are the dangers and drawbacks of those kinds of ranges? But without any more questions, I'm going to thank you again for attending. We really appreciate it. We also appreciate Werfen. Werfen sponsored this. The reason that you didn't have to pay a registration fee was because Werfen was willing to sponsor the website so anybody could join, and we thank them for their support. All right, looking forward to seeing you again in a future Westgard webinar. Have a good rest of your day. Bye. Still be registering. Hmm.
Hey, you're right. If the park go up there and say, people will be making themselves sick to take a ride with them. Actually, look perfect at the place up down. Show everyone that we're